So this is question number 4. Okay, so you have this compound. Okay, this is whenever you see CHO. Okay, please actually take note. When you see CHO, we always think that this is going to be aldehyde. Okay, aldehyde. So we are going to actually suggest a name, give the name. So here, if you have C, so I just put C there. Okay, and I have CH3, CH3. CH3, so 3 CH3s over there, and then connected to another one more carbon. Okay, and then the carbon has CHO. Okay, don't get confused with alcohol. This is going to be CHO. This is aldehyde. So how do we name this compound? Quite simple. Find the longest carbon chain. This is going to be the longest carbon chain, so it's going to be 3 carbon compound, so it's propanal. Okay, it's a propanal. And then we have a methyl group and another methyl group attached to this particular carbon. So if this is propanal, this is automatically carbon number 1. This is going to be automatically carbon number 2. Okay, and then the last one will be carbon number 3. So these 2 methyl groups attached to this carbon number 2. So it's going to be 2,2 dimethyl. There shouldn't be any blank space over there, so I'll just dimethyl propanal.
Sir,
Yeah.
the carbon number 1 starts from where it is attached to the functional group, yeah?
Yes, it will start from the one that is attached to the propanal functional group, always like that. Okay, so if you are telling like it's a carbo, let's say we actually talk about carboxylic acid, for example. Okay, if this is a carboxylic acid and then there's more carbon there, if let's say there is happen to be 1 Cl over there, so if I want to actually find give the name, so automatically this is 4 carbon carboxylic acid, so it's butanoic acid. So because we refer to carboxylic acid, so this is 1, this is 2, this is 3, so it's 3 chlorobutanoic acid. So it will not become 2 chlorobutanoic acid. You have to start from the functional group. Okay, the same applies. Okay, when sometimes it's different. Okay, sometimes it's different. Like for example, if you're referring it as an alcohol, for example, when we say like if you have like this OH, then we say this one I'm actually not. Let's say I want to actually find out. Okay, what type of alcohol is this? So this one butanol, but butanol we have a lot of butanol. So in this case I have to actually name it with a smaller number. So if I put the 1 here, this will be 2. I can, if I put 1 2, then this will be 3. So I will always select the 2 because we are not attached to any other functional group. So this one is going to be butan 2 all, something like that, not butan 3 all. So you just take note of this. Okay, naming. Okay, state the hybridization of carbon atom labeled by this symbol over here. Okay, so this one to name to find out the hybridization is quite simple. Okay, by now you should know. Okay, if you just look at carbon, ignore the double bond, 1 2 3, it means you need 3 orbitals. Okay, the only thing that can we have learned about sp, sp2 and sp3. If you want 3 orbital, this one has 2 orbital, s and p. This one has 1s and 2p, 3 orbital, and this one has 4 orbital, s and 3p. So we want only 3 orbital, therefore the answer is going to be sp2. So that carbon is sp2 hybridized. But if they ask you, let's say the asterisk, this symbol, they put it over here, for example. Okay, what type of hybridization is this? If they ask you, then you count again. So it's 1, 2, 3, 4. So you need 4 orbitals. Okay, in order to get 4 orbitals, this will come in. So this particular carbon is going to be sp3 hybridized. Okay, I hope you understand this. This carbon is sp2 hybridized. So last time when you actually remember, oh, okay, if it is double bond, I think double bond you memorize, okay, single bond you memorize, okay, maybe you will get confused for this question, okay. You need to actually remember according to the number of orbitals, okay. That will be the best way, okay. Now the next question, okay, you have um, this one, two reaction sequences are shown, okay. So you have this, okay, aldehyde. This aldehyde, they undergo this reaction NABH4, okay. This one normally is done under alkaline solution, okay. NABH4 is a reducing agent, okay. So normally they will reduce to what? So aldehyde, okay, normally it's primary alcohol, okay, secondary alcohol, tertiary alcohol. Primary alcohol will be oxidized, okay, to give you aldehyde. Aldehyde will be further oxidized to give you carboxylic acid. Secondary alcohol, they will be oxidized to give you ketone. Tertiary alcohol cannot be oxidized. So now you are moving the other way around. If you have aldehyde, okay, so now what's going to happen is the aldehyde is changing back, okay, to be reduced to become primary alcohol. So it means I know that this must be primary alcohol, okay. Ketone, okay, can be also reduced, okay, to become secondary alcohol. Since there is only one step over here, you can either use, okay, two regions, the reducing agent, okay. One is alkaline NaBH4, and another one is you can also use LiAlH4 in dry ether, okay. You can actually use that. But okay, when it comes to carboxylic acid, okay, if you want to change carboxylic acid to primary alcohol, it involves two steps. Okay, you cannot simply use both of the reducing agent. You need to use one strong reducing agent. The only reducing agent that you use in your syllabus for carboxylic acid to change into alcohol is LiAlH4 in dry ether. You do not use NaBH4. Okay, remember this. Okay. So let's move on. Okay, here in reaction 1, they are going to be oxidized. So you can see aldehyde can be oxidized to become carboxylic acid. So this one is oxidized. So for oxidation, you can either use acidified potassium manganate or acidified potassium dichromate. Okay, acidified. Okay, make sure it's acidified. Yeah, you can use any of these two, and then you get the carboxylic acid. Now, once you have this carboxylic acid, there is going to be a reaction 2, okay, where I can see, oh, there's another oxygen coming in, okay, so I know there's a carboxylic acid, okay, then I have some other molecules over here. It's not carboxylic acid anymore, okay. So what I do, I can actually roughly justify that, oh, this is carbon. If I break this, okay, this is looks like a ester, okay. So if I break this, I will get like carbon, 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 carbon. So it means this is CH3, CH3, CH3. So I know this carbon bonded to 3. So maybe referring to this, okay. And then there's CO, okay, then CO, okay, CO. Then this part, definitely, if it is going to be ester, this is going to belong to carboxylic acid, which is this one, okay. So this one is must be the alcohol, okay, that is actually reacting, okay, with the it means this is the alcohol, the T, okay. It means the one that has carbon, C, another C, and then O, and then this one must be H. So this is going to be most likely the structure of T, okay, structure of T. So that is the alcohol. And then this one, I know this must be esterification. So when I do esterification, normally we heat under reflux, okay, heat under reflux, and then we use concentrated sulfuric acid. So all this you need to know in order to answer this question. Okay, so if you are not sure with this, then you will have a lot of problems. Okay, you'll be stuck. Okay, so reaction 1, okay, is an oxidation reaction. Identify, okay, the region and the condition for this reaction. So if I want to identify the region, okay, let's actually ask someone. Nicole, Trisha, can you actually help to identify? Cannot hear. Are you muted?
No, I don't know, sir.
Okay, Lavi, can you tell me? Identify the region. I think it's already there, the answer.
Yeah, acidified.
Yeah, acidified,
Potassium
potassium.
dichromate.
Yeah, you can just select any one. Okay, so let's say I take what Lavi said. So potassium dichromate. Is it 6 or 7? Potassium dichromate.
5.
Uh,
7. 7.
no,
7.
6.
Or 6.
If you actually choose the acidified potassium manganate, then it's going to be 7. Okay, if they ask you what is the observation, okay, potassium dichromate will change from orange to become green. Potassium manganate will change from purple to become colorless. Take note of this, okay? And then they say condition, okay, regions. When they say regions, yeah, so normally if it is acidified, maybe I want to actually show more that I know a lot of things to the person who's going to mark this paper, okay? Acidified potassium dichromate, okay, it means you just put in bracket what kind of acid, maybe H2SO4, okay, acidified. Okay, condition, okay, must be heated under reflux. For this question is 1 mark. Okay, if you just miss the conditions, what will you get? Even though you give the correct region, you will get 0 mark. Okay, it means you must actually mention heated under reflux. Okay, next, A is a solid at room temperature. B is an isomer, okay, of A. And then B is a liquid at room temperature. Let's actually look. A, okay, is a solid. They say, okay, this is carboxylic acid, it's a solid. Okay, then they say something. Let's actually draw, okay, to make it easier to understand. Okay, carbon, CH3, CH3, CH3. And then I have C double bond O, OH. Okay, this is A. I'm going to have CH3. Okay, then C double bond O, O, because in the middle, yeah, so this one will form like this. Then I have CH2, 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 and then CH3. Okay, I'll have something like this. Then they say that, okay, this is solid. This one is going to be liquid. Now, when we talk about something being a solid or liquid, okay, we have to refer to something to do with the melting point and boiling point, okay? So if just by using solid and liquid, which one do you think has higher boiling point or melting point? A or B? Gabriela, Nicole?
A has a higher.
Yeah, generally when it is actually higher melting point and boiling point, they tend to actually stay as solid. Yeah, stay solid if you want to compare. Okay, so that this one, okay, is going to be higher melting point, high melting point, high boiling point. Okay, when we talk about high melting point and boiling point, we are talking about intermolecular forces. So they say intermolecular forces. In order to explain about intermolecular forces, you need to identify whether they are polar or non-polar. Okay, you need to identify that. Okay, I just want to know, okay, whether, okay, this molecule, are they polar or non-polar? Okay, so what can you say about A? Is it polar or non-polar, Lavi?
A is
Compared to, let's say, hydrogen and oxygen, which one is electronegative? Do you know what is the meaning of electronegativity?
yes, the difference between the charges.
No, electronegativity is actually the ability, okay, ability to attract bonding pair of electron to itself,
Is
pair
is it
or covalent bonded pair to itself.
is it polar?
In this case, yes, A is polar. Okay, why? Because the electron will go towards O. Okay, and then when you look at OH, oxygen will also pull the electron. So this one is delta negative, and this hydrogen will become delta positive. Okay, so what happens here? Okay, this one is they will pull, and then this is also going to pull over here. So it's actually happening in the between, and then it kind of cancel out. There is no delta positive, there's no delta negative. Okay, so this one will become non-polar. Okay, so this one is a polar molecule. Now, when it comes to polar molecule, there is a possibilities, okay, because hydrogen and oxygen, if you have another molecule, hydrogen and oxygen, there is a possibility to have hydrogen bonding. Okay, hydrogen bonding is the bonding between hydrogen with NOF, nitrogen, oxygen, and fluorine. Okay, if you want more details about intermolecular forces, I just finished lesson with JC1. I have uploaded some videos on intermolecular forces. You can actually go and see. Okay, but anyway, the hydrogen, nitrogen, and oxygen, nitrogen, oxygen, and fluorine. Okay, if they are involved in the bonding, it means they are going to be hydrogen bonding. In this case, okay, they do have hydrogen bonding. Okay, it's a polar and hydrogen bonding. This one is a non-polar. It means we are talking about van der Waals forces. Okay, so explain in difference of physical state. When you explain, okay, A has higher boiling point and melting point compared to B. Then you mention about A is a polar molecule and B is a non-polar molecule. A has hydrogen bonding with other A molecules. Okay, hydrogen bonding, okay, N, okay, you can say N van der Waals forces, because van der Waals forces is actually for all, okay. And then B has only weak van der Waals forces. Hydrogen bonding requires more energy to be broken. Okay, therefore A tends to be in solid form. Okay, I think I'm very sure that there are enough 3 points over there to give me the full 3 marks. Okay, so you just need to mention that, okay, they are polar, hydrogen bonding. They are non-polar, only have van der Waals forces, and explain everything, okay, related to bonding, high melting point and boiling point and so on. You do not need to explain about electronegativity, okay, no need, okay, unless they ask, okay. So next one, okay, give a balanced equation for the reaction, okay, to form S, okay, so S, okay, is a primary alcohol, okay, so here if I just put CH3, okay, that's 3, okay, then bonded to carbon, then HO. And here what's going to happen, it means this is going to become alcohol, it means H will come here. So it means the CH3, 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 C, then this one will be OH, H, H. Okay, so it means that it will be CH3, 3, then there is C, and then H2, or you can actually put C, OH. I think CH2OH will be better. Okay, but it doesn't matter actually. Okay, CH2, CH2OH. Or I don't want to put the bracket also, it's still fine. Okay, so this will happen. Okay, so I just need to take that again. So probably I'll just take. Okay, I want to actually put it here. Okay, so let me actually rewrite. So here CH3, 3CHO plus H. Okay, this one we need to use this. Yeah.
I thought the C have two. CCHO.
Oh, so I made a mistake. Yes, there's another one. Okay, correct. So here, there's another C. So I'm going to get CH3, 3C, CH2OH. But when you write this one, okay, do remember when the H is coming in, you are adding, okay, the H. You are adding the H over here. Okay, one of the H. You also add another H over here. Okay, and then nothing else. Okay, so all is fixed. So there's no water coming out. Okay, so no need to worry about water. Okay, so you just need to make sure that, okay, it means there's nothing. Okay, so it means this one must be 2. Is that okay? So this part, okay, there's C. Okay, draw the structure of organic molecule T that reacts. Okay, just now I already draw. Okay, so I will just take here, but I will not draw exactly like this. Maybe we change a bit. Okay, basically you just take from here. So I will draw carbon, carbon, then there is actually 2CH3, OH, then must have one more H over there. Each carbon must have 4 bonds. So I just put H, CH3, CH3, OH. Okay, they didn't tell what structure, so I just draw any structure will do. Okay, suggest a catalyst for reaction 2. Okay, the catalyst is going to be concentrated sulfuric acid, heated under reflux, concentrated sulfuric acid. So write down concentrated sulfuric acid. Then next, this one is very interesting. In order to answer this, we will go and get your data booklet. Let me erase. Let me put it here. Okay, let's try to answer this using this. Yeah. Now, so here, okay, I have some X, Y, and Z are all isomers of this. Okay, so this is going to be, okay, if I just take this one is carbon, then CH3, 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 C11OH. Okay, so there are many isomers. Okay, so they say that X, Y, and Z, they are isomer of this. Okay, so they say that they have done some observation, okay, with this and this, but I think this one is complete. They say principal absorption in infrared spectrum is given. Now, what you can do, you can actually look at your data booklet and then identify first. Then we can actually remove some of the things that we don't need. Okay, 1715. Okay, you can see the data is arranged like this. If 1715, probably it's somewhere here. Probably somewhere here. Okay, 1715 probably here. Okay, not anywhere else. Okay, it means that I know that, okay, this might be ketone, aldehyde, carboxylic acid. So I will write down ketone, aldehyde. It can be carboxylic acid and, okay, carboxylic acid, and one more is ester. Now, I can actually eliminate two things over here. Can you tell me what are the two things that I can eliminate out of these four? Victoria?
Sir, what do you mean eliminate? Oh, the one.
Eliminate means we can remove. Out of these four, out of this
Oh, is it
1,
like
2, 3, okay, I can remove another 2 from here. Can you see here there is only one oxygen? Okay. If carboxylic acid means what? They have 2 oxygen, carboxylic
Yeah.
acid. So it cannot be carboxylic acid. Ester, they must have, okay, like this. Okay, there's also 2. I eliminate ester. So it means, okay, this one might be either ketone or aldehyde. Okay, but still not finished yet. I can still eliminate, or I can still narrow down to something. Can you see the reaction with Fehling solution? The reaction of Fehling solution, there is no reaction. Now, if there is no reaction with Fehling, okay, Fehling actually used to identify aldehyde. Okay, positive results means aldehyde. So it means now it's a negative result. Okay, this one definitely going to be ketone. Jody, can you understand what I'm trying to do over here?
Yes.
Yeah, so I'm eliminating aldehyde because, okay, there is no reaction. So I know now they're asking observation with 2,4-DNPH. Now 2,4-DNPH is used to identify carbonyl compounds, especially aldehyde or ketone. And this is ketone. So what do I expect to see over here? I will see a positive result. Okay, so Charlton, what is the positive result with 2,4-DNPH?
Orange.
Orange. Okay, so you I think in the book they say deep orange precipitate. Okay, or orange. I think in the marking key they say red or orange. Okay, but I just stick to one. Okay, deep orange precipitate is formed. Okay, deep orange precipitate is formed. Now let's actually move on to the next one, 1730. Okay, when you look at 1730, let's do it again. 1730 might be here, might be here, might be here. Okay, no, nothing else. Okay, so here, okay, I will actually put, okay, it can be again ketone. Okay, it can be aldehyde. It can be carboxylic acid, or it can be ester. Okay, again, I can always eliminate carboxylic acid and ester, okay, because there's only one oxygen. So ketone and aldehyde, but I have a red precipitate over here in the Fehling solution. Now, Fehling solution, generally, I think they are supposed to give you a brick red precipitate. A positive result with Fehling solution will be, okay, the only thing that will give you the positive result over here in carbonyl compound will be the aldehyde. So it means we are talking about aldehyde here. So here definitely is going to be carbonyl compound, deep orange precipitate. Now let's actually identify further, no reaction and so on, but let's actually look at these values. Okay, 3,200 to 3,600. 3,200 to 3,600, maybe somewhere here. Okay, so H bonded alcohol. Okay, I'll just put H bonded alcohol, ROH. Okay, and means they are talking about alcohol. 1630. Let's actually look at 1630. So if I erase this, 1630. Okay, still no, not here. 1630, maybe here. Okay. Okay, so here when I say alkenes aromatic compound, it means the only thing that I see over here is C double bond C. Okay, so I will just put C double bond C here. Okay, it means there is a C carbon-carbon double bond. 1050. Okay, let's actually look. There is only 1050 means here. Now, ester I cannot put. Okay, because ester has 2 oxygen. Ether, okay, is possible. Okay, but there is alcohol. Just now got alcohol. Now there's another alcohol. Okay, so it means this one is a confirmation that there is an alcohol. So now observation with Fehling solution, okay, is no reaction. It means it's just further confirming that there is no aldehyde. Okay, it means most likely it's going to be alcohol, maybe with a carbon-carbon double bond. Okay, and you can see there's another confirmation saying that this one is not going to be a carbonyl compound. Okay, so this matches. Yeah, this matches. So here complete the table. I'm very sure you get the 1 mark already. I told you the deep orange precipitate is done. Identify the functional group, okay, present in Y that causes the recorded observation with Fehling solution. So present in Y causes this, okay, is going to be aldehyde. Okay, or you can say CHO group. Okay, aldehyde group. Okay, that is the functional group. Okay, do not be general by saying carbonyl group. Okay, because carbonyl group can apply for both ketone and aldehyde. So just give directly aldehyde. Y has a chiral center and exists as a pair of optical isomerism. Okay, optical isomer. Okay, they say it's aldehyde. It means I know just now even in the beginning it's aldehyde. And then they say, oh, this one Y is a aldehyde, and then they say there is a chiral center. Now let's actually look whether this particular molecule itself, whether they can actually give you a chiral center. Chiral center means carbon that can be attached to 4 different groups. I'm very sure that this is not a chiral center because 3 same groups. So can I rearrange this molecule so that it will give me a chiral center? Okay, so if I try to rearrange, okay, maybe the carbon and carbon, C double bond OH, this one definitely will come towards the end because it's an aldehyde. So I have another, this 2CH3, okay, can I actually put it somewhere else? Okay, so maybe I can put CH3 here, okay, and then this one definitely not chiral center, this one 2H cannot, so maybe I put another CH3 here. Okay, if I do this, okay, I'm planning to get a chiral center. Let's see whether this one will give me CH3, CH3, 3C, CHO. I have the CHO, okay. So how many total carbon that I need? I need total of 3 plus 2, 5 carbon. 1, 2, 3, 4, 5. 5 carbon is there. This one is hydrogen. This one is hydrogen. Hydrogen. Okay, how many hydrogen? 9 plus 1, 10 hydrogen. 1, 2, 3, 4, 7 plus 3, 10. Okay, and 1 oxygen. So this one is the molecule that I'm looking for. Why? Because I just created, okay, this particular molecule. This is going to be one group. This is another group. This is another group. This is another group. So the chiral center is this carbon. Okay, so if I just bring this over here, okay, let me actually paste it here first. Okay, here Y has a chiral center, exists as a pair of optical isomer. What is meant by chiral center is only one mark. Okay, a carbon compound. Okay, a carbon atom that is bonded, with 4 different groups. Okay, 4 different groups. Yeah, I think you just say 4 different groups. I think it's okay already. Okay, draw the optical isomer of Y using conventional 3-dimensional representation. Conventional, it means the one that we always draw. Yeah, so carbon CH3, another line, then it's CH2 CH3, so maybe I'll put C2H5, easier. Okay, and then there's going to be hydrogen. I put hydrogen, then dotted line, then it's going to be CHO. So draw the mirror image of that. Okay, C, then CH3. Okay, so this one will be CHO. This one will be, okay, if you want to actually face this side also doesn't matter. Okay, facing this side. So this one is going to be H. Okay, then dotted C2H5. Okay, this one is going to be the conventional 3-dimensional representation. So still have not completed, still going on. Okay, so here they have, okay, a branch carbon chain. It shows a geometrical isomerism. Okay, so now Z has a branch carbon chain. You have a look at Z. They say that they have the OH and then carbon double bond C. Okay, so it means that, okay, we know that it is also a branch. Okay, they say branch carbon chain. It shows geometrical isomerism. Okay, it means definitely there is like this. Okay, geometrical isomerism exists only when you have double bond, and then it's a branch carbon chain. Okay, so let's actually look at something that can actually give us, okay, some sort of geometrical isomerism. Okay, there is going to be 5 carbon. Okay, so let's actually put maybe CH3 here. Okay, I have another CH3 here. Just try around. Okay, and then I need another one more carbon. Okay, maybe I just put, okay, one more carbon here. So maybe CH3. Then this one is hydrogen. Okay, something like that. So I'm just still trying. Okay, still trying. But take note, okay, in order to have geometrical isomer, the carbon, okay, must not be bonded to the same groups. Okay, cannot. Okay, so this one, okay, might not be possible. Okay, so C double bond C. Okay, just keep trying. Okay, what else you can actually put over there? Okay, but do remember I mixed just now. There is OH. Okay, there's OH involved over there. So let's say I have this one is going to be OH, and then here is CH3. I have CH3 here. 1, 2, 3, 4. So maybe another. Okay, I think if I put CH3, not possible. Yeah, I think I'll just put hydrogen here. If I put hydrogen here, then I will have to put another carbon here, CH2OH. Maybe I'll try like this. Okay, it's still under my thinking process, yeah, how to do this, yeah, how to do this. So I just came across with this. Now I can double check, okay, whether it's possible or not. Okay, the reason why I try around without the CH3, because I don't want, in order to have cis and trans, the carbon must not be attached to the same group, okay? So it must be different. This one is different, okay? So this one I draw something like a trans isomerism, yeah? So if I just count, okay, 1, 2, 3, 4, 5, 5 carbon is okay, fine. Is it branch? Okay, I can see some branches over here, okay? So this one is already branch. Okay, if it is long carbon chain, okay, if this one is a long carbon chain, this is a branch, it's a metal, okay, so still okay. And then H10, let's count whether I have H10, 4, 7, and 10, yeah, oxygen is 1. So I know that this is going to be my structure. I'm happy enough already, okay. This is going to be my structure. So complete the table, okay, with the bond responsible for each absorption. I think just now we already completed the table, okay. It's ROH, okay. The bond responsible is going to be alcohol, okay. So you can actually just put OH, okay. 1630. 1630 is carbon-carbon double bond. Okay, carbon-carbon double bond. 1050, okay, is going to be alcohol. Okay, just put alcohol. OH also. Okay, if you want to put ROH, OH, doesn't matter, it's still alcohol. Okay, so we want to draw the skeletal formula of Z. Okay, just now we actually put this. Okay, if you want to draw, I think I went and saw the way that they draw in the marking key. So I will change a little bit, okay, because I think when skeletal formula to represent, let's say double bonds, they like to draw something like, they put the double bond like this. Okay, they start like this. Okay, it means this one is done. So this is carbon, this is carbon. Then you have one more carbon going going that side. So one more carbon going that side. And then this carbon, and then this one, there is another carbon going to this side. Okay, another carbon going that side. And then this carbon is bonded to H, and no need to show. And then there's OH. So just, I think they actually, rather than going down like forming zigzag, they actually put something like this. They just put like this, make it nicer. Okay. And then, okay, it means that this is carbon. Okay, it means that is carbon. And then they actually put the CH3 here. So this is another carbon. So there is another one that is going here. Okay. And then here bonded to hydrogen, no need to show. Okay. So this will be the skeletal formula. Okay, of Z.
So we cannot draw the zigzag one, yeah.
Can, definitely can, but this one, because I saw from the marking key, so I want to teach you guys to follow this one. Okay, I do not because in the marking key, some examiners, they follow 100% from the marking key. They are a bit rigid, and you can see that sometimes if you draw the zigzag, it looks a bit different than this. So and also the marks are 3 marks. Okay, I just don't want you guys, because the examiner didn't see properly, I don't want you guys to lose the mark. So it's better for us to learn to follow the marking key. Yeah, because this one is a recent paper. Okay, so let's actually follow the recent way of them marking. Yeah, so that's why I'm teaching you about this. Okay, so let's actually follow. And then here, okay, I think it's going to finish anyway. So you can see here, it's a carbonate group. Okay, so Charlton, can you tell me, okay, this one is what mechanism of this reaction?
Nucleophilic substitution.
Ayo, no lah.
Wait.
Addition.
Addition.
Okay, nucleophilic substitution is for alcohol and halogenal alkanes. Okay, so this one is nucleophilic addition. And go and read about this. How do you get HCN? Okay, HCN is prepared in situ. Okay, it is prepared in situ using sulfuric acid and NaCN. Please go and read. Okay, so you are going to get the ACN. Okay, so here they want you to draw the mechanism. So X, okay, X contains carbonyl group, X reacts. So is that X? Let's actually just take the X itself. What is X? Oh, they actually mentioned this. Okay, I can actually get the X directly from there. So here, okay, if you have X means they have C2H5, C2H5 bonded to carbon. So you have another C2H5. So this one OH and CN means there is going to be double bond O. Okay, so this one is going to be the X. C2H5, C double bond O, C2H5. So I'm going to have reaction with the ACN. So HCN, I will just draw like this. Okay, this one will go here. Okay, the electron will go here. So they will create CN. Okay, so dotted, dotted, minus. Okay, and then you have H plus. So what happens next is going to be this electron from here to will go here. So this one will become delta negative. The carbon now will become delta positive. So what's happened next is going to be this arrow will go towards the carbon. Okay, so the next thing is you will have C2H5, CO. The electron, since they went over there, this is going to be negatively charged, C2H5. So the CN will come over here, CN. So we know that there is H plus there. Okay, so this electron will go towards H plus. So you will get that. Okay, these are the reactions that you are going to have. Okay, state the role of NaCN in this reaction. Why we use NaCN? Basically to provide CN in the beginning. Okay, this one please go and read more. Okay, HCN is poisonous. Okay, if it is poisonous, okay, and it's difficult to change into CN. So initially what they do, they actually use the NaCN, okay, to give you a little bit of CN. Then once it started, okay, this reaction can proceed and then continue. So the role of NaCN over here is going to function as a catalyst. Okay, it's a catalyst. Okay, that's it.